Hi students, this is Dr. Shanthi, Professor, RMK College of Engineering and Technology. In this presentation, we are going to study about log periodic antennas, which comes under the Unit 4 of Antennas and Wave Propagation. Frequency independent antennas. Log periodic antenna comes under frequency independent antenna. As the name indicates, this type of antenna, it will remain fixed in size or size will vary in proportion, right? And over the entire bandwidth, what happens here is the impedance, the pattern, polarization and gain of the antenna remains constant over the entire bandwidth, and hence the name frequency independent antenna. Frequency independent concept was introduced by Victor H. Rumsey. What it states is the impedance and pattern will be frequency independent if the antenna shape is specified only in terms of angles. Log periodic antenna is an example of frequency independent antenna. As I told you in the previous slide, impedance and pattern, they are going to remain constant as a function of frequency. And one more point is the frequency independent antennas, they expand or contract in proportion to the wavelength. Right? The geometry of the log periodic antenna, as the name indicates, the electrical properties repeat periodically with the logarithm of the frequency, and hence the name log periodic antenna. Right? Now the variations of the properties over one period gets repeated every period. The reason a log periodic antenna involves a basic geometric structure that is repeated but with changing size of the structure. The structure changes with each repetition by a constant scale factor, so the structure expands or contracts. Log periodic antenna. Now look at the diagram. When you look at the diagram, this is the point where you give in your excitation. Now this is one dipole element. This is the next dipole element. You look at the feeding what we give. We crisscross it when I move on from one element to the other element. Now when you look at the diagram, the size of the dipole lengths increase proportionally. L stands for the length, R stands for the spacing of the element from the origin, right? S stands for the spacing between adjacent elements. Say for example, let us talk about Ln. Ln is the length of the nth dipole element. Rn is the distance from the origin to the nth element. Sn is the spacing between Rn and Rn plus 1. Right? And now listen here, look here. So what happens here is all the ends of the dipoles, when you see for each of the dipole, when you join the two extreme ends, the subtended angle, the angle subtended is going to be alpha, right? So this is why, or this is the structure of your log periodic antenna. Now, when we look into the diagram, what we saw is the dimensions increase in proportion to the distance from the origin, right? And number of dipoles of different lengths and spacing are fed by a balanced two-wire transmission line, which I explained you in the previous slide. And what is constant? The included angle alpha is constant. And when we move on, the lengths and spacings are graduated in such a way such that the dimensions of adjacent elements bear a constant ratio to each other. Now when we looked into the diagram, the region of operation was divided into three. That is, when L was lesser than lambda by 2, L equal to lambda by 2, and L greater than lambda by 2. When L is lesser than lambda by 2, I call it as inactive transmission line region. What happens here is the L region, this region, the elements behave as a, or they offer high capacitive impedance, and hence what happens when there is a high capacitive impedance? The element current is small and leads the base voltage by the transmission line, supplied by the transmission line by 90 degrees. So what happens here is the currents in the elements of these region are small, and hence small radiation is there in the backward direction. Now active region is the region of our interest, where length is equal to lambda by 2. The impedance offered by the dipoles in this region are resistive, and the element currents are large and in phase with the base voltage. So what happens here? There is a strong radiation towards left in the backward direction and a very little radiation towards right. And the third one is going to be inactive reflective region for L greater than lambda by 2. Here this region offers inductive impedance, right? So this is going to offer inductive impedance, and there is a very small wave that is present. Even that is reflected back towards the backward direction, which is reflected by the active region. Okay, so L lesser than equal to lambda by 2, it offers capacitive impedance. The region of interest is active region, where L is equal to lambda by 2, where it offers strong radiation towards left in the backward direction. Okay, right. And inactive reflective region, it is inductive, and even it offers small radiation towards backward direction. Even that is reflected back once again by active region. As I told you earlier, you have what is called a scale factor or design ratio represented by tau. Now, what did we see in logarithmic antenna is there is a proportional increase, that is, it either expands or contracts by a regular factor called a scale factor. What is the scale factor? R1 by R2. What is R1? The distance of the first element from the origin. Okay, the ratio of R1 by R2 is equal to R2 by R3, or is nothing but Rn by Rn plus 1. This is nothing but equal to tau. The same way, what it means with respect to lengths, it is L1 by L2, which is equal to L2 by L3, which is equal to L3 by L4. So, which is nothing but Ln by Ln plus 1. So, this is nothing but called as the design ratio represented by tau. Right. Now, in the same way, with respect to spacing also, I can tell Sn plus 1 by Sn is equal to Ln plus 1 by Ln, which is equal to 1 by tau, which is equal to k. Design of log periodic antenna involves finding out the equation for sigma and alpha, right? Right, where sigma is nothing but spacing with respect to wavelength lambda, right? And alpha, once again, that is angle subtended. It is 2 inverse of 1 minus tau by 4 sigma. So these two are the design equations that are used in the case of log periodic antenna. Now the frequency range in which the log periodic antennas operate is around 30 megahertz to 3 gigahertz, which belongs to very high frequency band and ultra high frequency bands. The main advantage is it is compact. Gain and radiation patterns are generally varied according to the requirements. And as the name indicates, frequency independence is obtained here. It is used for high frequency communications, used for particular TV receptions, and used for all-round monitoring in high frequency bands. Thank you, students.